Alright, so this is part 1 of lesson 2.5, inclined planes. So the learning target, I can identify forces acting on an object on an inclined plane. I can draw a free body diagram of an object on an inclined plane. And hopefully at the end of this lesson, you'll be able to identify the formulas needed to calculate the force of gravity parallel and the force of gravity perpendicular, which are these two symbols right over here. So let me circle them. So these are going to be new for us, these guys right here, and we're also going to be able to identify the direction of the normal force. So when we think of an inclined plane, you've definitely seen them every day of your life, and most commonly where we have seen them are ramps or some sort of hill going up or down, right? That's an inclined plane essentially. So what an inclined plane does, or is rather, is a tool used to move objects from one height to another. So if I have an object right here, I can move it up the ramp, make it go over here. Likewise, I could also go down the ramp, right? And it also allows for the movement of an object without lifting it directly against gravity. So using a ramp is actually a lot easier than you trying to pick something up and go up the stairs. If you remember from your history course, you learned about the Great Pyramids of Giza, and the Egyptians used ramps to push those big pieces of blocks that now make up the pyramids in Egypt. So ramps have definitely been around way before, this class we're talking about it. More importantly, the rate at which they slide down, right, is dependent upon how tilted the surface is. So if it's greater the tilt, the faster the object will slow down. So usually any object that's placed on an inclined plane, it wants to slide down. It doesn't really want to stay up at the top. So for example, this guy, he wants to actually slide down instead of staying there at rest at the top. Like I said, the rate at which they slide is dependent on this tilt. What that tilt means is just this angle, right? The angle we call theta. Okay, so if I have a bigger angle here, right? This is the angle that we're going to be looking at. If I have a bigger angle here, right, that means, let's say if I drew a new thing and if I drew a new surface in, now I have a new angle theta, and now the object is right here. It definitely wants to slide down more than in the original picture. So if I have a bigger angle, that object is going to slide down faster. That's essentially all this is saying. And in terms of, principal forces acting on the object, we know that the force of gravity always pulls, straight down. Okay, and if you remember, the alternative name for the force of gravity is called weight. That's why we could say objects weigh 780 newtons. Weight is a force. It is just the force of gravity. Okay, so like I said, it's going to pull it straight down. So sorry, drew these little other boxes in. Didn't even realize they were there. Okay, however, this force of gravity, because now we are on an inclined plane, we are no longer on a flat surface, we have to break it up into different components. So before on a flat surface, we used X and Y. Here we can no longer use that. We have to use perpendicular and parallel. So the first one is the perpendicular force of gravity. So this isn't a minus sign right here, so I'm just going to cross it out. So the force of gravity perpendicular is equal to the force of gravity times cosine theta. I'm going to let you know, this is not on the reference table. Okay, so you will have to remember it. And likewise, the same formula for the parallel component that is also not on the reference table, you are just going to have to memorize it. So perpendicular, what that means is whatever that perpendicular line is meeting with the surface or something it contacts, it's always going to make a 90-degree angle. Okay, so perpendicular, all it means is 90-degree angle, and it's this upside down T symbol. That just means perpendicular. Okay, the next component is called the parallel component of gravity. So that's Fg parallel equals the force of gravity times sine of theta. So again, I'm going to cross this out because it looks like a minus sign. So just like before, we said that this symbol is perpendicular. This symbol means parallel. Okay, and how you can memorize that is parallel has two L's that looks like the parallel symbol. So I'll label this one as perpendicular, just so that we know. Okay, so the job of the parallel component is to pull it down the slope, okay, or the inclined plane. That's its job. The perpendicular component, its job is to pull that object into the surface of the inclined plane. So it pulls into, the parallel pulls down the surface, okay? So that's a pretty big idea. So hold on, let me see if I can get rid of this guy. So if you look on this diagram, you can see that FG parallel slides down the slope, okay? And then FG perpendicular pulls into the surface. And then there's one important relationship after this. The normal force is no longer going to point straight up because, again, the surface has changed. It's not a flat surface anymore. It is an inclined plane. So now our normal force is going to be perpendicular to the surface of the plane. So it's equal and opposite in magnitude to the force of gravity perpendicular. Okay? So because it's perpendicular to the plane, it is also going to make a 90-degree angle. So essentially here you can say, just like we used to say the force of gravity is equal to the normal force on a flat horizontal surface, we can now say that FG perpendicular equals Fn. Okay? So they're equal and opposite in magnitude. So for example, let me pull this down. This is how you would draw it on a free body diagram. So again, you have Fn, Fg. They are making 90-degree angles with the surface. Okay? And that's a very important idea. This big component right here, this is where you're getting your other components, this guy and this guy. Okay, so FG is broken up into the parallel and perpendicular components. We don't use X and Y anymore because we are not on a flat horizontal surface anymore. So it wouldn't be appropriate for us to use or for us to break it up into those components. However, we can now say perpendicular and parallel. And likewise, the formulas for those components will not be on the reference tables, but we are familiar with cosine theta and sine theta. And that's pretty much it for this part.